Ever wondered how your smartphone screen or your TV display shows such sharp, vivid images? It's all thanks to a special material called liquid crystals. These fascinating materials do much more than create electronics. They're the inspiration for our institute WPI-SKCM² at Hiroshima University. Join us now as we explore how liquid crystals sparked our curiosity about the fundamental nature of matter, the building blocks of everything, including ourselves, driving us to uncover nature's secrets and design materials that improve the world. While exploring the world of liquid crystals, our director, Professor Ivan Smalyuk, was struck that some of the most fascinating things about these materials was the presence of knots. At first glance, knots might seem unrelated to cutting-edge science. But knots and their relatives, like links, braids, tangles, and weaves, are found everywhere, from your knitted sweater to DNA, proteins, and even groups of animals. The idea of knots even applies to things that are harder to imagine, from the smallest particles that make up everything around us, all the way to the structure and expansion of the universe. Knots are also studied in math, in a field called topology. And in liquid crystals, the knots would simply come undone, but interestingly, they are stabilized by an asymmetry of the molecules known as chirality. And just like knots, this asymmetric feature, chirality, is also found everywhere in nature. Here's the puzzle. Knots and chirality appear all around us, but each field, like math, physics, chemistry, and biology, approaches these patterns from its own perspective, and no single discipline holds the full picture. By combining ideas and methods from all of these fields, we can better understand how knots and chirality work in nature and use that knowledge to design solutions to complex problems. We're already learning to harness these knots for real-world impact. For example, this transparent aerogel, which can be used to create super-insulated buildings. By creating super-insulating materials, we can create buildings that waste much less energy and help to reduce climate change. Not only do we aim to create new materials specifically designed to tackle problems like climate change, but our researchers, who are working together from all over the world, are also pursuing knot and chirality questions in their respective fields that will help address other global challenges, such as diseases, storing data, and more. WPI-SKCM², untying the mysteries of the world and ready to save it by solving its knotty problems.